What is up, everybody? Welcome back. Chapter 4. So, if you remember what we did last time, we looked at the method referred to as spin stabilization as an effective way to stabilize the rotational motion of a spacecraft by solely spinning the spacecraft about its major axis of rotation. Doing so ensured that the motion would remain stable as time goes by, even though it might be disturbed by some small quantities in terms of angular velocity components in the body fixed reference frame. So we were disturbing that equilibrium spin away from it and observing that the motion remained stable thanks to the fact that the spin was about the major axis of rotation. That is the major axis rule. But you say, okay, in practice though, it might not be practical to always be restricted to spinning a spacecraft about its major axis, just due to the fact that the camera could be located along an axis of the body fixed frame that if you were to spin the spacecraft about its major axis, the camera would swing all over the place instead of looking directly, say, at the sun. So how can we go about that? Or how could we circumvent the major axis rule? The idea here is to use a dual spin stabilization technique, which implies that we're going to put a solid mass inside the spacecraft known as a wheel that is going to be rotating at a constant rate about a constant axis with respect to the body fixed reference frame. And that wheel will then add additional angular momentum about its axis through which it is oriented. Doing so will allow us to turn any principal moments of inertia of our spacecraft as the major axis, okay? So in other words, if a spacecraft, due to its configuration, it would be beneficial to spin it about, say, its intermediate axis of rotation, but you know that that won't lead to a stable rotational motion. The trick will be to insert inside the spacecraft body a wheel, so a solid block of aluminum or whatever kind of metal you're using to design the wheel, along the intermediate axis of the body fixed reference frame, such that by spinning this wheel about this axis would increase largely the angular momentum about the intermediate axis of the reference frame, and thereby turning the intermediate axis into what I call a virtual major axis. It is still not the major axis because the inertia about the intermediate axis in terms of numerical values would still probably be the one in between. Well, okay, you've added the additional wheels, that would change it slightly, but maybe not enough to get the intermediate moment of inertia to be larger than the major moment of inertia. But just through the fact that this wheel is spinning and thereby increasing the angular momentum, it could be turned into a virtual major axis of inertia, and thereby spinning the spacecraft about this axis would give a stable motion, okay? So this is exactly what we're going to look at in this subsection in 4.3, which is dual spin stabilization. Dual spin because now a wheel inside the spacecraft would be spinning, and then the spacecraft itself would be spinning about the same axis. Dual spin stabilization. Okay, so the first thing we're going to do here is to rederive the equations of motion, now taking into account this additional mass within the spacecraft that is rotating at a constant rate about a constant axis. Now keep in mind that this is a little bit more complex than simply spinning the spacecraft body about the major axis without having to add any moving parts inside the spacecraft. Yet, adding a single wheel that spins about a single axis at a constant rate is not that difficult, okay? Because you won't need to accelerate the rotational speed of the wheel or decelerate it in real time, nor changing the axis of the rotation for the wheel. Now, the former refers to a reaction wheel. So that is a wheel which is accelerated and decelerated in real time to change the internal momentum of the spacecraft on the fly. Whereas the other one, where the axis of the spinning wheel is changed, is referred to as a control moment gyroscope. Both of these devices are referred to as actuators and are quite a bit more complex than a single wheel, fixed axis, fixed rotational speed, which is what is used for dual spin stabilization. So again, one level up in complexity compared to spin stabilization, yet offer us advantage of spinning the spacecraft about any axis and yet resulting in stable motion. So 4.3.1 equations of motion. Now, before I dive into deriving those equations, I just want to draw real quick what we are dealing with here. So let's say you have a rigid spacecraft that has this kind of shape. That spacecraft obviously has a center of mass that coincides with the origin of its body fixed reference frame, Bx, By, Bz, such that the inertia measured around this unit vector would be Jx, Jy, and Jz in terms of mass distribution, okay? And within the spacecraft now, we are adding a spinning wheel, like that. A chunk of mass that spins at a constant rate about a constant axis of rotation that we shall denote A. Okay, so for example, in that case, if you would have Bx as the major axis, which say, boy, it'd be really convenient to spin about Bz instead because my camera is looking in that direction. So I'd like to maintain the line of sight between the camera and an object of interest to be stationary. Because if I were to spin the spacecraft about Bx, which is the major axis, then the camera would be swinging all over the place. And that wouldn't be very practical. So to maintain the line of sight here, you say, boy, I'd really like to spin about Bz, but Bz happens to be, say, the minor axis. Gee, I know that minor axis isn't very stable in terms of passive stabilization. So what I'm going to do is that I'm going to add a wheel along the axis of interest to ultimately increase the net momentum of the spinning spacecraft around Z, plus the momentum of the wheel about the same axis, add the two together to get this axis of rotation with a larger amount of momentum than this one, and thereby creating, again, what I refer to as a virtual major axis here. This will always remain the minor axis in terms of shear mass distribution within the spacecraft body, yet because of the additional momentum created by the wheel in that specific direction, this turns into our major axis, and therefore spinning the spacecraft in that direction would yield a stable rotational motion. Okay, so that is the key idea here. And again, I have added an additional variable to the picture, which is the spin axis of the internal wheel component that we've added to our spacecraft A. Okay, and we're going to refer to the wheel speed, angular rotation, as omega s in terms of scalar, and its angular momentum to be h of s. Okay, so let's see how this turns my previously obtained equations of motion into. Well, first we'll have to look at the angular momentum vector h to do that, and express the total angular momentum vector in the body fixed reference frame, like that. Okay, hb, where my hb now is not only function of the spacecraft platform itself, but also influenced by the wheel's rotational motion about its spin axis. How? Well, the spacecraft platform's contribution is going to be the same as previously, so j omega b. But then we're going to have plus hs in terms of scalar, so that would be the norm of the angular momentum of the wheel with respect to the spacecraft platform, In which direction? Surprise, surprise, in the direction of rotation of the wheel, which is a vector like this. So again, this is for the spacecraft's contribution to the net angular momentum, and that would be the wheel's contribution to the net angular momentum. Okay, that makes sense. Now what we're going to do is go back to how we had obtained Euler's equations of motion from the angular momentum vector back then. And the first thing was to apply the transport theorem to get H solid dot and equate that to the net torque applied to the spacecraft. Okay, so we're going to say that H dot is going to be equal to the same as the torque, obviously, equal to, from the transport theorem, I'm going to write that this is H hollow plus omega b, or just omega, vector, cross product with the angular momentum vector. Okay. But we know that H hollow dot has to be expressed in the moving reference frame, which is our body fixed reference frame. There is no other choice here. HB solid dot like that. Or I can say that this is the same as simply transpose of body fixed reference frame vectrix times the time derivative of HB. And surprise, surprise, what I have here in the curly brackets from before, that was HB in terms of components. Time derivative of all that. J omega b plus HS times A vector. Okay. That's easy peasy for us because we know about the chain rule, which we can apply. So time derivative of J times omega b plus J, the inertial matrix, times the time derivative of omega b plus the time derivative of HS times A plus HS time derivative of the spin axis of the reaction wheel. Oh, sorry. That was all in components form. I shouldn't have a vector here. A in, okay, just A. Oof. Yes, it almost got me. Okay, well, what do we know? We know that if we were to select a body fixed reference frame such that the x, y, z unit vectors of that reference frame are aligned with the principal axis, then the time derivative of our inertial matrix would be equal to 0, which is what we're doing here, okay? So all in all, we're getting transpose of vectors b. That was just the norm, so scalar equal to j omega b dot. Well, we said that the wheel was spinning at a constant angular velocity, constant omega s. And also, we're probably assuming that the wheel's inertia about its spin axis is constant, unless it gets broken and pieces start flying off, but then you have a much more bigger problem than the stabilization of the spacecraft, okay? So all this to say that HS and omega s are both constant, and therefore this is 0. But I also said that the spin axis expressed in the body fixed reference frame, which is this, was constant. Okay, this wheel is not moving around with respect to the red reference frame here. It's always stationary with it, with respect to it. So its time derivative is also equal to 0. So ultimately all you have for H hollow is just J omega b dot. Okay, I know how to plug this back into my Euler's equation of motion on top here. Okay. And I'm going to then skip one step and do it real quick, and that is to express that in terms of components in the body fixed reference frame, equivalent to torque, body fixed, equal to HB solid dot. Well, that one is not in the body fixed. This is the inertial derivative, so that would be in the ECI, but we don't really need that. I'm going to start from here. HB dot plus omega b skewed with HB like that. We know, and that the torque in body fixed is J omega b dot. That's what we've obtained here for HB dot, okay? Plus omega b, that doesn't change, but what changes now is the angular momentum in the body fixed reference frame due to the added reaction wheel. And from before, we had seen that that was just J omega b plus HS scalar times A components in the body fix, right? That was our starting point to get HB dot. We started from HB and then took the chain rule of that and canceled a bunch of terms. So HB is the spacecraft or the spacecraft platform's contribution plus the spinning wheel's contribution within the spacecraft. So that gives me the torque equation. Okay, from there we need to go back to our previous assumption that said that our objective was to analyze the motion in the torque-free environment, and therefore we're going to set tau b all equal to zeros, like that. Also, we're going to select a principal axis, the body fixed reference frame. Principal axis, body fixed reference frame FB, such that we'll be able to deconstruct that into three equations very easily. And for the purpose of the follow-up demonstration, let's select the components of the axis of rotation of the wheel within the spacecraft expressed in the body fixed reference frame. And we're just going to define it along the BZ unit direction as it was drawn in the figure previously. If you consider this, and that, it means that you could rewrite that matrix equation as being 0, 0 for the torque equal to Jx omega x dot plus Jz minus Jy times omega y omega z, as we had with our previous version of Euler's equations in terms of three scalar equations. But this time the difference is this additional term that comes from the wheel's contribution, okay? Similarly, along the y-axis, we will get Jy omega y dot plus Jx minus Jz omega x omega z minus this time Hs omega x. And finally, for our z equation, and again, our z equation will be slightly different than the other two because we had arbitrarily selected the wheel's axis to be along z, and that changes things. So specifically, we're going to end up with Jz omega z dot plus the difference in principal moments of inertia, like this, which multiplies omega x, omega y without any wheel's contribution, okay? So just as a trick to ensure that those equations are derived properly for dual spin stabilized spacecraft is that the axis that you select for the rotational axis of the internal wheel mechanism will always give you that equation along that specific direction to be the simplest, so without the wheel's contribution, okay? And that's just from the skew-symmetric matrix operator. If you were to do this linear algebra development by hand, here I just gave you the result, but it's only a matter of multiplying matrices together, okay? Not that big of a deal. Cool. So, because we've located the wheel along the BZ axis, it probably means that that was the axis about which we intended to rotate the spacecraft about. Okay? So for that reason, I'm going to select, boy, I need new markers. I'm going to select our equilibrium condition to be omega x equal to omega y equal to 0, and omega z equal to some constant value, again denoted by nu. And nu is, as per before, a constant. Is that really an equilibrium point? Well, to make sure, plug these conditions back into those three equations, and you would see that indeed you then get omega x dot equal omega y dot equal omega z dot equal to 0, which is the equilibrium condition. Okay, and that is a constraint that you need to demonstrate for any equilibrium point that you happen to select. If you don't end up with that, those three things equal to 0, it means that this equilibrium that you've selected is not in equilibrium, okay? Nice. Now, whether or not this particular equilibrium point as selected here is stable is yet to be determined, and that will be the bulk of the follow-up work. So essentially, we're going to do exactly as we did with the spin-stabilized development, but this time using different equations of motion obtained because of the fact that now we've added a wheel to the picture, or in other words, we've added two terms here to our equations of motion. Okay. Not a problem. Not a problem for us, because we understood the process done in the last lecture, right? Or we know. I think I have to switch to red. Sorry about that. It's a little bit aggressive, I think, red. But that's just the nature of thing. I'm out of blue. I'm out of black. And green is getting quite faint. So I'm stuck with red for the time being. Okay, apologies for that. So then, based on these equations, the next step is to look at the stability analysis of our equilibrium point that we've selected, and see if by perturbing it by a small amount, we're going to get back to equilibrium or generate an asymptotically stable motion, or just keep oscillating with constant amplitude around the equilibrium. That would be a stable motion. Or maybe we'll see that adding the wheel makes us diverge or become unstable with time. Heads up, that's not going to be the case, otherwise that would be useless to do this passive stabilization technique demonstration, okay? So we're going to get stable at the end of the day. No worries about that. Well, let's demonstrate it. So let's first perturb the motion away from the equilibrium point by just tiny amounts, denoted by epsilon x, epsilon y, and here the nominal rotational speed about bz unit vector, plus again some small disturbances, pushing it away from the equilibrium. Now we need to insert these back into those equations of motion, okay? So our omega x, omega y, omega z derivatives will simply be turned into epsilon x dot, epsilon y dot, And that one is slightly different. So we're going to get still with jz times mu dot plus epsilon z dot, because all this is for omega z dot, plus this difference in principal moments of inertia times now epsilon x, epsilon y, or omega will just be turned into epsilon, epsilon y, epsilon z, and here it's epsilon x, epsilon z. Here we had plus minus, plus hs. Was it x or y? It was y, omega y, so that it is epsilon y. And here we had minus hs, omega x, so hs epsilon x now. Okay? So all I did was to substitute my omegas with what they are when they get perturbed away from their equilibrium values. Or this is equal to 0, obviously. Because we have no torques, external torques applied to the spacecraft. Good. And now it's just the same process all over again, yet for different equations. So again, we'll assume that any epsilon square will be approximate to 0 because we're just slightly perturbing the motion away from the equilibrium. We are also considering that the nominal speed at which the spacecraft spins about the BZ direction is a constant. And that's it, okay? Such that mu dot disappears. And you're left with jz, epsilon z dot. Those two terms multiplied together are canceled out. What did I do? Oh no. Sorry, it's not that simple. Because these two terms were omega z, and omega z, we had mentioned before that these were mu plus epsilon z. My bad. Mu plus epsilon z. Okay? So those two are canceled out, right? This is the square of epsilons. Boom, 0. Such that the last equation is simply jz epsilon z square, or dot, sorry, equal to 0. And the first two would turn into jx epsilon x dot plus jz minus jy. And now the epsilon y times epsilon z terms cancel out, or are approximated to be equal to 0. So we're left with this plus hs times this equals 0. And similarly for the y equation, plus jx minus jz epsilon x times mu simply, minus hs epsilon x equal to 0. Y mu hs y x mu minus hs. Yeah, that works out. So now we end up with these three new equations of motion. Well, the obvious thing is that about the z, whenever the spacecraft gets disturbed by a little amount away from its nominal spin, not a problem, because we're going to get the perturbing factor, epsilon z, that won't grow with time. And in fact, this will remain constant, such that you would end up for omega z equal to nu, plus that small perturbation always there, nagging you a little bit, but yet becoming just a constant. would end up spinning about z at mu plus epsilon z and stay there. Okay? That's good news. So this is stable motion. So we have to shift our focus now to the first two coupled linear differential equations, these. And I'm going to do the exact same thing as we've done before. The only difference again here is that we have additional terms in the equations. So what I'm going to do next is to rewrite these equations slightly differently by having epsilon x dot equal to, I'm going to divide now everything with jx, and I'm going to factor out my epsilon y out of these two terms, okay? Equal to jz minus jy over jx. All this times mu 2 mu, thank you, it's a little bit better, plus hs. No, I don't want to solve it, I just want to write it this way. Okay, so just dividing everything with jx, and then factoring out my epsilon y, and then this is going to be multiplied with epsilon y, and all that equal to 0. Okay? Z minus y over x. Actually, the hs term is also over x though. I might be tired. That's okay, I've got a green pea waiting for me on the side here. Probably pull that up in a couple of minutes. Second equation, epsilon y dot plus jx minus jz times mu minus hs. All this times epsilon x, and all this divided by jy, and obviously equal to 0, torque-free environment. All right. I'm going to make my life easier, and I'm going to define a constant denoted by lambda. I'm going to say that lambda, just close this guy up, it's going to be defined as being arbitrarily equal to jz plus hs over mu. Okay? Such that I can then rewrite these equations, making use of this new definition here, as epsilon x dot equal to lambda minus jy, this guy, over jx. Okay? And this multiplying mu, and times epsilon y. All this equal to 0. Okay? And then my epsilon y equation is going to be not equal, come on, plus epsilon y dot plus jx minus lambda over jy times mu times epsilon x, all this equal to 0. That looks quite a bit familiar, doesn't it? Because we have the derivative of our two dynamical variables of interest plus a scalar that multiplies the other variable of interest. And those two equations are coupled together this way, which means that I can just draw a parallel between the results I had obtained with the spin stabilized and compare those with the dual spin stabilized situation. And specifically, if you look at what we had obtained for the spin stabilized case, spin stabilized versus dual spin stabilized. What we had back then, in the previous lecture, was epsilon x dot plus jz minus jy over jx times epsilon y equal to 0. Now here I have something very similar, because I have epsilon x plus lambda minus jy over jx then I had the new term as well in there, mu times epsilon y equal to 0. And if you were to compare the y equations, you would see something very similar. So those two are for x, and then for y, spin stabilized versus what we're doing now, dual spin stabilized. We had epsilon y dot plus jx minus jz over jy, all this times mu times epsilon x equals 0. And now what we've just obtained was epsilon y dot plus jx minus lambda over jy, all this times mu times epsilon x equal to 0. So it doesn't take a genius to realize that those equations are actually equal. The only difference being that we've replaced the principal moment of inertia corresponding to the desired axis of spin of the spacecraft and also the spin axis of the wheel with a lambda, okay, in both equations. That is the only difference. Okay, so then am I allowed to draw the same conclusions? Yes, absolutely. So instead of applying the same conclusions in terms of jz, smaller or greater than whatever, we're going to say lambda, okay? So before, we had seen that jz needed to be larger than jy and also larger than jx to obtain poles on the imaginary axis. That's the best we could have done with spin stabilized. Because otherwise, if those two inequalities weren't satisfied, we would end up with poles, either two poles at the origin of the complex plane, or poles on, or one pole on the right-hand side of the complex plane, and those were situations or cases that didn't make us happy. Remember the happy face and the sad face here. And we had also determined that either this or jz smaller than jy, and also smaller than jx would be satisfactory, but because of our discussion about the major axis rule, we know that this is only a theoretical result, and therefore it doesn't work in practice. We're going to scrap that out. So now, then for dual spin stabilization, instead of talking about jz, now we have some sort of virtual moment of inertia created by jz and the wheel's contribution along this axis. And that is referred to lambda greater than jy and lambda greater than jx. Those are the two inequalities that we need to satisfy to obtain a stable rotational motion about bz direction, even though bz might not be the major axis. Because this, if you remember, the definition was the original jz, the spacecraft body, but plus the wheel's contribution. Okay? This term here changes the value of jz, if you will, and turn that into what I call, again, a virtual principal moment of inertia about bz. Okay? So all we have to do to maintain stability is to make sure that this virtual moment of inertia about bz happens to be the largest of all three entries. Although before spinning the wheel, maybe jx was the largest. But the trick here is to make sure that you spin the wheel fast enough by increasing this contribution such that the net moment of inertia about the axis of interest, bz in that case, becomes the dominant one. Okay? If you stop the wheel, then that situation could change upside down. But as long as the wheel keeps spinning at a high rate, you could maintain those two inequalities being satisfied at all time and then spin your spacecraft about any principal axis, regardless of which one is the largest, because you know the trick is just to put a wheel inside the spacecraft and spin that wheel fast enough such that the axis, the spin axis of interest becomes then the major axis when you consider the wheel's contribution. Okay? Easy peasy. That one was fast because we didn't have to rederive all equations. Essentially, we took advantage of what we did in last lecture and just reapplied the same conclusions we had drawn here, but this time swapping only the moment of inertia of the body with body moment of inertia plus the wheel's contribution to this term. Okay? Hope that makes sense to you. Hope you learned something new today. As usual, keep up the good work. And I'll see you in the next lecture where we're going to dive into gravity gradient as another passive stabilization technique for rotational motion of spacecraft. Take care. See you soon.